Welcome to my channel. My name is Opubo. For those of you new to the channel, I say to you welcome. For those of you returning, I bid you welcome back. Good to have you return. You are well appreciated. In this channel, I present various ideas and designs of technologies, mostly from the Technology IP Bank. Digressing, however, for a moment, before making a deep dive into the matter of plastics chemicals recovery, I implore you to please click the subscribe button below now if you have not as yet subscribed to the channel. Go ahead and subscribe by simply clicking on the subscribe button below. The subscription would cause the system to keep you informed by notification of the next presentation the moment one is published, and also, of course, help me to more consistently continue to elicit the peace dividends of conservation economy. Now back to the presentation. Position of plastics does not readily occur. Empirical observations and study of the degradation of plastics over long periods of time have shown no detectable degradation often occurs. So, given the need for the elimination of the health hazard and attendant filth image of the plastics when it's strewn all around, the option that has been considered has been the burning of plastics. Naturally, fires does destroy most things, and as such, the burning of the plastic has been practiced in some cases. However, even that approach to the destruction of plastics has raised many issues. The burning is often incomplete, and so the ambient air gets fouled up and is obnoxious to the people living around the area. The unburned particles often get trapped by rain dropped during rainfall and ends up polluting the water. The properties around the area where the burning is done also get coated with plastic soot that make the houses look unappealing. Of course, this happens because at burning the plastics, vaporization of large quantities of the plastic occurs before the burning actually starts, and even then, the oxygen to carbon relation within any continuum of the burning space is not stoichiometric And so there will always be incomplete combustion burning of the plastics. And the leftover are the culprit for all the above listed issues. Therefore, recovering the core hydrocarbons is probably preferable and necessary, such that the plastic get recovered as a resource, and with the result that the filth caused by the discarded plastics also get removed without the consequential issues. The approach to accomplishing such would be to create a stoichiometric reaction context, and with any reaction occurring at the molecular level only. In effect, the reaction have to be contained until all the hydrocarbon units of each molecule of the plastic has participated in the reaction. Rationally then, the requirement calls for the use of a chemical reactor equipment in which to contain the reaction as well as control the product's effluent time. The use of Newtonian particle sizes as in the current burning operation should be discontinued, and the size of the particles engaging in the reaction be changed to Brownian sizes or microparticles. Further, the microparticles must be fully wetted at all times in order to prevent airborne dispersions of the microparticles. Now, guided by the technology for the decomposition of polychlorinated biphenyl, a technology for the decomposition and recovery of the constituent chemicals have been developed from the integration of technologies already available in the IP bank and is as shown in the image. Actually, plastics are powderized and dissolved to the extent possible in ethanol, and the resulting non-Newtonian fluid is pumped into the technology, which converts the plastic microparticles into various organic acids and organic gases. By design, the technology consists of thermosiphon reboiler, electrolyzer, programmable chemical reactor, cooler condenser, fractionating distillation system, gas separation unit operations, flash equilibrium steel, decanter, ion separators, and at least 2 storage tanks, and as always, of course, process controller system. Looking at the schematics, the design can be grouped roughly into 4 columns of equipment. The leftmost column has 2 equipment sets, with the one at the lower left corner being the thermosiphon reboiler, and above that, a unit operation set of 3 gas separators. To the right and the second column is at the top the cooler condenser. Below that is the flash equilibrium steel, and below that is the electrolyzer. In the next and third column is a set of 2 ion separators at the top. Below those is the decanter, and below which is the programmable chemical reactor. The rightmost column are 2 storage tanks at the top, and the fractionation distillation column with the boiler below it. During operations, water is pumped into the thermosiphon reboiler, where the water boils and produces steam, and which flows into the electrolyzer and is broken up into hydrogen and oxygen. The hydrogen flows into the programmable chemical reactor, fed at the top part of the base, and the ethanol in which the plastics have been dissolved or are entrained is pumped also into the programmable reactor at input below the hydrogen input. The hydrogen atoms react with the inorganic atoms in the plastics and form inorganic chemicals, including possibly acids. The inorganic acids, of course, may play the role of catalyst for some organic chemical reactions, depending on the contents of the ethanol mixture. The carbon-hydrogen units also react with the hydrogen and form various hydrocarbons, including mostly methane, ethene, and some propene and other large chain molecule hydrocarbons. The small chain hydrocarbons are predominant because of the powdering of the plastics. Some of the reaction products, hydrocarbons, become gases, while some remain dissolved in the liquid. The liquid in the reactor is pumped into the flash equilibrium still to forcibly separate out the dissolved gases, but in the process, as always, also cause some of the liquids to vaporize. The gases stream of the reactor, which also includes some of the vapor of the liquid substances, flows out of the reactor and is combined with the gas stream formed in the flash equilibrium still, and the both flow into the cooler condenser, where the stream is separated into liquid and gases resulting from the condensation of the liquid vapors into liquid. The liquid of the cooler condenser and the flash equilibrium still also get combined and flows into the decanter. The gaseous effluent stream of the cooler condenser flows into the gas separation unit operations and are separated into each gas type. The liquid in the decanter separates out the acids, alcohol, and organics, with the hydrophobic organic chemicals floating on the top, and while being decanted flows into the distillation boiler where it gets boiled up and as vapor flows into the distillation column, with fractionation occurring and the components sent into the storage tanks. The acid mixture of the decanter, however, is pumped into the ions separators, which sequentially separates the ions solution into pure separate acids. Clearly, as by this process delineation, there can be uniform acceptance at this time that there is in fact a technology for large-scale continuous decomposition of all types of plastics, enabling the recovery of the constituent chemical substances and hence permits the utilization of the chemicals as a resource available to every geographical space and hence enabling of conservation economy. Notably, recovering the plastics as short-chain hydrocarbons, including ethene and propene, is most effective for use as these chemicals form the foundational resource chemicals for the chemical industry. Although the detoxification of the microfibers in the human body may be challenging, at least continued dissolving of microfibers into drinking water can be mitigated by the adoption of this technology, both from the environmental cleanup and conservation economy considerations. The materials of construction of the chemical technology, of course, being mainly steel, the technology provides opportunity for the utilization of discarded metal parts in every region and allows for the extensive reuse of process equipment otherwise not used and deemed waste. As such, the technology supports the operational conduct of conservation economy. If interested in licensing this technology, please send an email to me. The email address is put in the pinned link below, as are other useful information. Regarding licensing consideration, there are some notes that should be of interest. Worthy of note that the gas separation unit operations are developed from the air gas separation equipment and number as many as there are gas components. Similarly, the acid separation ion separator equipment also number as there are as many acids to be separated, which of course depends on the plastics. I wrap up the presentation now by saying to you, thank you for being here, and I appreciate your coming to listen and to view the presentation, and hope and expect that you would consider coming back for the rest of the future technology presentations. The fact is, even if you do not necessarily adopt any of the technologies presented in the presentation, any one presentation, some might just change your perspective of society and life. Until the next presentation, I wish you be well.